In this video, we're going to focus on whole number addition, just an introduction, and some models and properties of whole number addition. Before we start, however, it's probably a good thing to talk about what are whole numbers. Whole numbers are a set, that's important, that it's a set of numbers, and I often think of them as the counting numbers. Here's a set of whole numbers, 0, 1, 2, 3, 4, 5, 6. It's the numbers you often count with. But you don't often start with 0, obviously. Very few people start with 0. So it turns out that the numbers 1 through sort of 1, 2, 3, the counting numbers, those are called the natural numbers. But the whole numbers are the natural numbers with a whole on the end. That's the easy way to remember it. So 0, 1, 2, 3, and those are the whole numbers. Well, in the elementary classroom, there are two common models, I'll call them, for illustrating essentially the addition of whole numbers. The first one, and I'll do this, say, in the context of 4 plus 2. When you're trying to help young students understand what is 4 plus 2, the best place to start, and the way most teachers start in the very young grades, is to use a set. So in other words, what I'm going to think of, I'm going to think of two sets, a set A and set B. And set A is a set that has, let's say, 4 objects. So I've got, say there's 4 squares. Set B is a set with 2 objects. And I'll do those in different colors. Say those are circles. So I've got 2 blue circles. 4, I don't know what that would be called, mauve, all right? Mauve squares, 2 blue circles. In the set model of addition, it uses some set notation, set language. These sets are disjoint, meaning they have nothing in common. So if the two sets are disjoint and you combine them, and the operation for combining them is called a union. So A union B is the process of combining A and B into one superset, I guess we'd call it. So let's do that. A union B would create another set when I combine those two sets, put them together, and what they would have is they'd have 2 blue circles, and we would have 4 mauve squares. So it turns out when these numbers are disjoint, or when the sets are disjoint, that the number in that essentially the number in the union equals the number of elements in set A plus the number of elements in set B. When you add those together, that equals, if the sets are disjoint, the number of elements in A union B. Oh, but that illustrates the concept of, in a set way, the concept of addition. If you take 4 elements, then, and if you have essentially, if you got 4 elements in set A, 2 elements in set B, and those sets are disjoint, then we can say that 4 plus 2 is equal to the number of elements in A union B, or it's the number of elements that when you put the 2 disjoint sets together, it's the number of elements in that combined superset. So the sum is what it's called. 4 plus 2 equals the number of elements in A union B. All right, let's do 4 plus 2 on a number line, which is another common model. So 4 plus 2, and just a little notation or language for you as well. 4 plus 2 is considered the sum. It's the sum of 4 plus 2. And each of these individual numbers is called an addend. All right, so just using the right language. So if I want to add 4 plus 2, we've already seen we can take 2 sets, that's the addition of 4 objects in one, two objects in the other, you can have the kids count, and it would be 4 plus 2. Count them when I put the sets together, 6. On a number line, you can think of taking steps along the number line. If I have a starting point, I'll think I'm going to start at 0. And I take a 4 steps to the right. So 1, 2, 3, 4. So that represents your 4. Okay, now what I'm going to do is I'm going to add or continue in that way. I'm going to continue taking steps, and I'm going to take 2 more steps. So if I take 2 more steps from my 4, so this is the plus 2, where you get to, where you land, is your sum. So on the number line, 4 plus 2, if I start at 0, 4 plus 2 would be that ending point, 6. And that's a little more sophisticated conception of number, by the way, because in this case, numbers don't represent numbers of objects, but they are sort of abstract things on a number line. But you can also think of those as steps that students are taking. 4 steps to the right, continue 2 more steps. How far is the student? 6 steps away. So it's very easy to illustrate that with children. Finally, we've got some common properties of whole numbers, which we'll talk about in this class. And the 4 that we're going to go through, at least for now, one is called the closure property. The closure property says that if you take any 2 whole numbers and add them together, you get another whole number. So 2 plus 3, that sum, 2 is a whole number, 3 is a whole number, that sum is a whole number by the closure property. The commutative property, and it's not commutative, it's commutative. If A and B are whole numbers, then A plus B equals B plus A, or in other words, if I take 2 plus 3, that's the same as 3 plus 2, and both of those would equal 5. The identity property of addition, this set, technically what it says is that the whole numbers have an identity, an additive identity, which is 0. What that means is if you take any whole number, say 15, because that's a whole number, and add 0, that's the same as if you take 0 plus 15. Well, that's commutative, but that equals 15. Identity means that if you add 0 to any number, you don't go anywhere. You get back the original number. The final property is an important one called the associative property. And what that says is that you can add numbers in different ways and get the same result. So if I take 2 plus 5 plus 3, I can take 2 plus 5, which is 7, and add 3, that would give me 10. Or I could have done it like this. I could have said that is 2 plus 5 plus 3, which is 2 plus 5 is 2 plus 8. That also gets me 10. So if you associate these whole numbers in different ways with different parts of this expression, they're still equal to one another. We're going to finish off this brief video with just a little bit more on my favorite property. You might say, well, how do you have a favorite property? I don't know. I think it's a neat property called the closure property. And I'm not going to talk about it in terms of whole numbers. That's fairly straightforward. It says that if you add 2 whole numbers, you get another whole number. But I'm going to talk about it in general in terms of sets. If I tell you that a set is closed under addition, so that means that if I take any 2 values in that set and add them together, I should get another number in that set. So if I tell you that the set is 0, okay, well, is that closed under addition? Well, that means if I take any 2 numbers in the set, well, you can pick the same one twice. If I take 0 and I add it to 0, what do I get? I get 0. That's in the set. So that set 0 is closed under addition. How about the set 0, 1? Well, that looks like pretty similar to what we just did, but it turns out that's not closed. Because if I take 1, which is in the set, and add it to 1, which is in the set, I would get 2, which is not in the set. So the first one is closed under addition. The second set is not closed because I can take two values and add them together and get 2, and 2 is not my set. So it's not closed under addition. Here's one that is. How about multiples of 5? So I'll call that F for 5, 0, 5, 10, and on and on and on. Goes on indefinitely. It's an infinite set. Okay, well, take any two numbers in there. Well, like 5 plus 10. 5 plus 10 is 15. That's also in the set. Take another, 25 and 35. 25 and 35 would be 60. That's also in the set. If you take any multiples of 5 and add them together, you get another multiple of 5, which is in the set. So that one is closed under addition.